This conference will now be recorded.
All right, and welcome everyone to the week 3-4 S2S webinar that is held jointly by the OAR Weather Program Office and the National Weather Service Office of Science and Technology Integration. I'm Bonnie Brown. I'm one of the staffers from the Weather Program Office. And this is a monthly webinar occurring on the first Monday of every month. But next month, we are not going to have one because we don't want to conflict with the AGU meeting. So Maureen, let's pull up the logistics. Okay, so we're going to have a talk today from Ben Kirtman, and then the second talk will be from Carl Schreck. These are both PIs funded by the Weather Program Office, among other sources. Please mute yourself if you're not speaking. We have a discussion document and we'll put the link to that in the chat. It's a Google document where you can type in your questions and then we can bring them up in an organized way to the speakers when they're done, or have them look at the questions afterwards. And you can always also put questions or comments or such in the chat. Okay, so now I'm going to turn it over to Ben.
Okay, hopefully people can see that.
Yes, we can.
And you can see that too.
Yep. Mm-hmm.
Okay. Just get my pen in case I need it here. So I'm going to talk about the role of air-sea coupling in the SubX, and there's sort of two parts to this talk. The first part is more fully cooked, if you will. It's a paper that's in the second round of review in weather and forecasting. And the second part is also related to air-sea coupling, but that's much more speculative. We're still working on that element. And I want to acknowledge my collaborators, Kathy Pigione, Rachel Zielinski, and Leo Siquiera. So just as an outline, the first part of this talk is really looking at how well the SubX models do during the DYNAMO intensive observing campaign in the Indian Ocean. Initially, we were really focusing on the initialization of the MJO events, but it turned out that the propagation characteristics turned out to be a little bit more interesting, so I'm going to emphasize that. And we're looking at two particular MJO events that were well observed during this DYNAMO campaign. MJO1, which is going to be an uncoupled event, and MJO2, which is the literature has sort of been labeling as a coupled event. I don't want to confuse the coupled MJO events and uncoupled MJO events with a big part of this analysis, and that is separating the coupled SubX models from the SubX models that are with using prescribed SSTs. So that's a subtlety here, and maybe it's not a subtlety, it's an important thing that you need to keep in mind is that there's sort of two notions of coupling, one being the MJO events themselves in terms of what mechanisms are associated with them, and the second is the models, some models being coupled and some models being uncoupled. And then the second part of the talk is getting more into air-sea feedbacks, local air-sea feedbacks, sort of this question of who's forcing who in terms of the atmosphere forcing the ocean enforcing the atmosphere. And I want to motivate that by some curiosity as we look at the SubX forecast, and that is how the signal variance seems to evolve as a function of lead time, sort of the motivation for sort of digging into this, and I'll explain as we get there. And then if I have time, I'm going to just show you one specific example of some particular coupling and feedback that's critical for forecasting. Okay, so these are time longitude sections in the Indian Ocean from the TRIM data during the DYNAMO field campaign. This one here is this uncoupled MJO, It's the first MJO that occurred during the field campaign, and the literature is sort of labeled, like I said, a lot of studies looking at it, and the argument is air sea feedbacks really didn't play a big role in that particular MJO. And then the second one is this, we're going to refer to as the coupled MJO, and there are certainly hints here, although it's just one event. There's a lot, the propagation characteristics are a lot more robust in the coupled MJO. Okay, in terms of the SubX models that we're going to be looking at, those models that are highlighted in the light green here, those are models that are uncoupled. The SST is prescribed. It typically is damped persistence, but it's some kind of prescribed SST. And then all the models that are highlighted in blue here are coupled models. And we're going to treat them, we're going to look at them separately. And so you can see we have on the order of 19 ensemble members for the uncoupled models, and on the order of about 40 ensemble members for the coupled models. Okay, so just moving forward, this is that uncoupled MJO, Indian Ocean, across the basin near the equator. Is average for 5 north, 5 south. Time is running up the page this way, and so you can see the propagation in the rainfall of the MJO event. This first panel over here, this is the ensemble mean of the ensemble members that are from coupled models. And so you can see there's certainly an indication that it's guessing that there's this period of enhanced rainfall in both the coupled models and perhaps even in the uncoupled models. There's this period of enhanced rainfall, but you don't see any kind of any hint of the propagation characteristics that you see in observations. This is based on the ensemble mean here. In this work, we started to think about this a little bit. How do you, instead of taking the ensemble mean, you really want to consider all the ensemble members, and so the best we came up with the metric of considering all the ensemble members is to plot the probability of there being rainfall. And so this is probability that ensemble members actually predict there's going to be rainfall. So you see a slight enhancement, not a big surprise given the ensemble mean, that the coupled models are producing enhanced rainfall and then a quiescent period and enhanced rainfall. But I can't really argue that the uncoupled models didn't capture that enhanced rainfall. But in neither case do we see any hint of propagation. No propagation. All right, coming to the coupled MJO, again, 5 north, 5 south across the basin, trim estimates. This is again the coupled MJO a little bit later during the DYNAMO observing period. This is the ensemble mean of all the ensemble members from the coupled models, and this is the mean from all the ensemble members from the uncoupled model. So again, the initiation seems to be there. That the large-scale circulation seems to be kicking off an event at approximately at the right time of year. But again, no clear propagation characteristics. When there's certainly a hint in the ensemble mean that there might be some propagation, a hint, not too strong. When we look at the probability, however, we definitely see a stronger suggestion of that eastward propagation, and we're largely unable to detect that in the uncoupled ensemble members. Again, so this is for that coupled MJO, that event where the argument is that coupled feedbacks are playing a big role in the maintenance and propagation characteristics of this event. And there's a hint that, in fact, the SubX coupled models are able to do a somewhat better job at capturing those propagation characteristics. So digging in a little bit deeper, this is a little tricky metric, so I'm going to take a minute to explain this. What I'm doing here is I'm taking the precipitation in this region between 60 degrees and 90 degrees east, so this sort of region here, highlighted this region 5 north, 5 south, so it's an index. So I've now converted that into an index, and I'm calculating the lag-lead relationship between precipitation and SST. So when we have a lag here, or minus values in this lag-lead relationship, that means SST before the rainfall maximum on day 0. So it's SST leading here, and this is SST after the rainfall maximum. has occurred. This lag lead plot. So you can see in advance of that, the rainfall in this uncoupled, again, this is this uncoupled MJO. In this uncoupled MJO in advance, you see warm SSTs in advance, and then rainfall kicks off, and then you see cold SSTs following. And you see a strong hint of that in the coupled model. Warm SST in advance and reduced SST following. The uncoupled models are unable to, largely are unable to capture that relationship, even though precisely the role of coupling in this event, this uncoupled event, is quite a bit more ambiguous. Let's take the coupled event. So here things are a little bit different. So again, same rainfall index over this region, 5 north, 5 south, same kind of lag lead plot. Again, SST and precipitation, strong correlation in advance, weaker correlation, and you see some hints of that propagation. And again, when you look at the SubX coupled models, you see that basic characteristic. And you know, the cold afterward also. It's not perfect by any stretch of the imagination. There's lots of uncertainties here, but at least there's a greater, you know, qualitative as opposed to quantitative, but qualitative similarity between the coupled models and the observational estimates as opposed to the uncoupled models. Whether that actually translates into a better forecast of the MJO and the MJO teleconnections downstream remain an open question. Now this is you know, getting a little bit closer to the dynamics, and so this is doing pretty much the same thing. Again, lag lead with precipitation, but in this case we're looking at U850, and I would argue that the coupled models and the uncoupled models look more like each other than they do look like the observations. They're sort of missing these strong precursor signals, doing a little bit, you know, maybe a little bit better during the event itself, you know, the contemporaneous correlation, but the precursor signals are relatively weak for either the coupled model or the uncoupled model. So maybe, you know, if you squint your eyes, you might say there's some features that look better in the coupled model, but I think you're hard pressed. When you take a look at the uncoupled, the coupled event, again, this confusion, I apologize for the confusion in the language, coupled models versus uncoupled models, coupled MJO versus an uncoupled MJO. I apologize for that confusion in the language. But again, you see a little bit different relationship in the observations as expected, a lot more propagation characteristics associated with this coupled MJO, and a slightly stronger indication that the coupled SubX models are capturing that to some degree. Although there are hints, definitely there are hints in the dynamical relationship here, the 850 millibar wind, that the uncoupled models are doing okay. There's certainly something there, but you know, this real strong indication of, you know, that you really see in the observations is certainly a little bit stronger in the coupled SubX models. Okay, so this question of who's forcing who, the first thing I want to do is kind of motivate why we started thinking about that, and then I'm going to talk about a little bit about how we started to look at this. And so here's the motivation slide, and let me just sort of explain what I'm looking at here. This is looking at the week 1 versus week 4 precipitation signal variance. So it's a ratio, and so when this variance is less than 1, so this is only plotting areas where the variance is less than 1. Where the variance is less than 1, it says that the week 4 variance in rainfall is larger than week 1. So as a function of lead time. So what this is saying is that the signal variance is increasing as a function of lead time. And so this surprised us, by the way. This surprised us that we saw such a big increase in the signal variance in these forecasts in the deep tropics. That was a surprise to us. I'm not sure I fully understand it, why that would be the case, but this seems to be quite robust, that the signal variance is increasing in the deep tropics. to me, that suggests some kind of spin-up dynamics is happening in the convective precipitation that's going on. Something has to spin up, but that definitely surprised me. This bottom plot is again showing that ratio, but now it's only showing values greater than 1. So this is when week 1 has larger, the signal variance in week 1 is larger than week 4. And of course, in the deep tropics, it's nearly 0. And there's nothing plotted, and that's because the week 4 variance is larger. But you see in the exotropics, there's this ubiquitous increase in the week 1 variance over week 4. And so one of the things we wanted to think about is, why is this precipitation signal variance falling off so rapidly in the exotropics? And the hypothesis that we're putting forth in the analysis, at least, that we're performing here, is that it had something to do with air-sea coupling. Okay, and in fact, we sort of drift into the notion that ocean eddy activity may actually be important. Whether we can make any of those hypotheses stick as a strong indicator remains to be tested. So this is, like I said, work in progress. And so this comes back to this question: whenever you think about coupled modeling, coupled models in terms of local air-sea interactions, anyways, who's forcing who? And there's two typical ways that this has been looked at in the past by a number of different authors, but this result is from some of my colleagues a few years ago. But one thing to look at is locally, what's the SST latent heat flux correlation? And the way this correlation is being plotted is positive values indicate the ocean is strongly forcing the atmosphere. And this is between latent heat flux and SST. So you see in the far eastern Pacific, El Nino-like SST forcing the atmosphere. But in the other parts of the ocean, you see a very different kind of response, much more where the atmosphere seems to be forcing the SST. And then perhaps not too clear, but you see sort of ubiquitous increases in ocean forcing the atmosphere in the observations in the exotropics. The bottom panel here, this is now really trying to make the argument the atmosphere is forcing the ocean. So now we're looking at how the SST tendency is related to the latent heat flux. So if you have big latent heat flux, you expect a tendency in SST. And so you see a strong negative correlation throughout much of the world's ocean, and that's the atmosphere forcing the ocean. Now, this second set of panels is sort of pushing that to the limit and saying, okay, what about local SST precip relationships? Again, making the argument that when it's positive here, the ocean is forcing the atmosphere, and then here where SST tendency and precip. Now, I think it's a physically much stronger argument when you do this in terms of SST and latent heat flux, and when you think about it in terms of SST and precip, it's much more of a qualitative thing, because there's so much remote forcing of precip that can go on. Nevertheless, you see some consistencies between these two plots that make it interesting. And we were just wondering if there's something about the coupling processes in the forecast that we could identify that are helping us explain this changes in variance as a function of lead time in the forecast. So this is then doing that precisely. This is the local correlation between SST and latent heat flux. And again, everywhere you see the bright red colors is suggesting the ocean is forcing the atmosphere, and everywhere you see sort of blue colors is, red colors, ocean forcing atmosphere, blue colors, atmosphere forcing ocean. And just for comparison, the argument I was sort of hinting at, but didn't really fully explain, was that, ocean resolution could play a big role in this. Ocean eddies have been shown on longer timescales to play a big role in seasonal and decadal forecasts in terms of SST variability driving the atmosphere. So we were wondering on these subseasonal timescales, do we see the same thing? And so I think the the biggest signal that we see here is the relative stationarity, if you will, or not a big change in the week 1 correlation versus the week 4 correlation in the high resolution model, but we see a pretty strong change in the week 1 versus the week 4 forecast in that correlation. And you can see it's really starting to light up those regions where the atmosphere is forcing the ocean, and that just doesn't seem to happen in the high resolution model. The other big difference, of course, is in these higher latitudes. You're seeing much more, much stronger hints of strong positive ocean force in the atmosphere correlations. We expect that on seasonal and decadal timescales. We didn't necessarily expect that on subseasonal timescales because it takes a while. You know, these particular set of forecasts are initialized with models that don't really resolve those ocean eddies, and so we were expecting that they wouldn't necessarily spin up quite so fast to capture that interaction, but indeed it seems to hang on to that. And then of course you know it's not a surprise, but these look fairly similar during week 1. The high resolution, the low resolution. We'd expect that they're both initialized with exactly the same source of observations. And then look, this is now looking at the tendency, and here I have to confess I don't understand what's going on in the least. You see this huge atmosphere forcing the ocean at the initial condition in the low resolution model, and so the similarity is between these two guys. Why that would be the case, I don't really understand why this would look less like a relationship. Again, I think you know, my thoughts are that this is the period of time, this week 1, this is the period of time when those eddies are really starting to spin up, and any kind of atmosphere forcing those eddies doesn't kick in until later. But that doesn't explain why the lower resolution model looks more like the high resolution model at week 4. So some curiosities coming out of this analysis that we can't fully understand. This is now just drilling down a little bit, you know, just looking at a particular region. Here's the North Pacific. And so this is a region where we know on seasonal timescales at least that the ocean eddies are really contributing to improved predictability and are actually forcing the atmosphere. And so you're seeing strong hints of that showing up in the week 4 forecast with the high resolution model, and definitely a decline of that correlation by the time that local correlation when you get to the week 4 forecast from the lower resolution model, the SubX resolution. And you can see it is in the first week hinting that relationship really is part of the observed characteristics of the climate system, sort of a proxy for observations we want. And again, this curiosity I have with I just don't really honestly don't understand why this strong similarity between the week 1 and week 4 of the 2 different resolutions. Interesting result. This is good. I'm ahead of schedule. This is the one example that I want to show to sort of end this up. And so let me take a few minutes. This is looking near the South America and the South Brazil current. There's a western boundary current. So let me just sort of walk you through these slides. This is days 1 through 15. These are SST anomalies in the high resolution model, low resolution model. You can see they're fairly similar. But what starts to happen in this region of this boundary current, this region of this narrow boundary current, it starts to really spin up. And you can see it's much warmer than it is in the low resolution model in this region. And when you look at the rainfall that goes along with these days 45 to 60 in this low resolution and high resolution model, what you can see is the convective precipitation really spins up along this current region, and it doesn't in the low resolution model. And in fact, you can see some of that convective precipitation even penetrates into land. So again, this is the argument that getting some of these detailed features in the ocean affect the atmosphere, force the atmosphere, and can have terrestrial effects in the near coastal region, which can turn out to be quite important. All right, The idea of the talk was really to look at air-sea coupling in the SubX and really take a phenomenological approach. So really, we're starting out not really purposefully not digging in and doing skill scores, purposely really just taking a phenomenological approach. Can we understand some of these differences, and can we attribute them to how the models are treating air-sea coupling? In terms of the MJO and the DYNAMO, I think we have a very suggestive result that during these coupled MJO events, the coupled model, the coupled SubX models tend to perform better at capturing the propagation characteristics. Although there are even hints during those uncoupled MJOs that the coupled models give some enhancements too, at least in how the rainfall connects to the SST. The second part of the talk was really digging into this notion of who forces who. We looked at the local turbulent heat flux SST relationships, precipitation SST relationships. We introduced this high resolution model, which I really didn't have time to talk about too much. And there are hints, and I would say just hints, that in some regions that high resolution model, the representation of mesoscale features, whether that be eddies or boundary currents, are giving a potential boost. But there's some real curiosities in terms of how the air-sea feedbacks are working as a function of lead time that we definitely don't fully understand. And I will stop there. Thank you.
All right, thank you, Ben. Let's see. No questions currently in the discussion document. So, and I don't see any in the chat right now. So while people think about that, we'll go on to our next speaker, Carl Schreck. Carl, I'm going to make you a presenter. All right. So again, folks, there's a link in the chat to a Google document, and you can type your questions in if you have questions for the speakers. That way, if we run out of time, they can still address your questions and you'll be able to see their answers. And yeah, you can find that link right in the chat there. If you don't have access to Google for whatever reason, you can still put your questions in the chat, or we'll see if we have a few minutes at the end to unmute and ask questions live. So Carl, I'll hand it over to you now. Thank you for taking the time to present today.
All right, and can you see and hear everything okay?
Yes, we can.
Excellent. Today I'll be talking about some work that I did with some colleagues, one Matt Janiga out at NRL and Steve Baxter, who until recently was at CPC, and trying to see what some of the main sources of subseasonal skill are in CFS V2. And this is work that you can find in MWR, the paper that came out earlier this year. So some of the kind of main things is kind of surprising to us is that most of the subseasonal rainfall skill actually comes from just essentially persistence and largely tied to ENSO. And I think portions of Ben's talk were a really good motivator for that, where a lot of the regions where we see longer term skill are areas where there's really strong correlations between the SSTs and the precip. The MJO, it does actually contribute some skill to rainfall primarily over the Indian Ocean, but there are impacts elsewhere. And I'm also very interested in equatorial waves, and equatorial Rossby waves in particular can help during certain regions and seasons, but they're not as broadly useful as the other modes. And just kind of as a motivator for this, there's a web page that I've had for several years now, nkix.org/MJO, where I have a number of these near real-time diagnostics of CFS forecasts for a bunch of different variables, looking at the MJO and various equatorial waves. And so the kind of centerpiece of this project was transitioning this into operations at CPC, but we were also looking to do a lot of skill verification on it to see how it could be most useful. And so kind of the main tool that's on the website, nkix.org/MJO, are these Hall-Mullers. In my case, time is going downward, and the shading are unfiltered anomalies relative to a daily climatology, and the contours are filtered for the MJO and various wave modes, primarily the MJO in black, low frequency background like a 120-day low pass filter in magenta, equatorial Rossby waves in red, and Kelvin waves in blue. And one of the things that we do that's unique here is we combine both observations with forecast data. So above that horizontal line, it's the recent observations, in this case OLR from the NCI Maryland CDR. And then in the future, below the line, there are CFS forecasts up to 45 days, and then climatology thereafter, in order to be able to do the Fourier filtering in real time. And in addition to the Hoffmullers, we also have maps of a number of varieties. You can pick your averaging window, region, wave modes that you're interested in. A lot of times I find it useful to focus in on just one wave, in particular the MJO, as I'll talk about more in a bit. You know, just focusing on the black contours, that's one of the things that we know the model is going to have more skill than perhaps other modes. So the verification that I did, I was focusing on the hindcast for CFS V2 from 1999 to 2010. And in this case, I was verifying rainfall anomalies. And these were relative to the TRIM 3B42 rainfall data set. And I kind of essentially did this with three different types of data sets. The one on the left is more conventional filtering, where you take the entire period of record for TRIM 3B42 and run the filter on the entire thing, so you don't have to worry about any endpoints with the filtering. In the middle is kind of my version of a perfect model. So in this case, I've got observations in the past plus 45 days of TRIM observations, and then climatology thereafter. And essentially what this shows is that even when there is data, you know, the filter isn't always going to match up exactly with the unfiltered anomalies. The contours and the shading aren't going to line up one-to-one. And also there are some effects from the transition from the end of the forecast, essentially, like the bottom of that second line where it goes from shading to white, where you switch from observed anomalies to climatology. That does have some impact even in the past on some of these filtered variables. So if you look closely, there are slight differences in the contours between the left and the middle. And then on the right is essentially what we're actually doing on the website, which is observations up until the first horizontal line at November 15th, and then CFS forecasts, and then climatology thereafter. I think this is actually this might be MJO2 from the DYNAMO event, if I remember right. And so I do this for the full 1999 to 2010 period of record, and then I do a 3-category Heidecke skill score, since that's what CPC primarily relies on, essentially looking at what's the probability of being above, below, or near normal. And I calculate that for the filtered variables for each wave mode, and then try to verify that against the shading, essentially against the observed terciles. And so this, to start off with, this is essentially the Heidecke skill score from the middle column. So this is if the model, essentially replacing the model forecast with the TRIM 3B42 data to just kind of see what's the effect of the filtering on getting an accurate forecast. And this actually was a little surprising and interesting to me that there's actually quite a bit of difference between the different filters on where and when, or where they're going to be most skillful. In particular, the low pass filter on the top is really, really skillful over kind of the central Western Pacific, the INSAR region. And that probably makes sense that if you have an El Nino, you're going to have really strong positive rainfall anomalies. If you have a La Nina, it's going to be really strong dry there. What was more interesting to me is that the MJO skill, and again, this is just based on the filtering and observations, not based on anything with the model yet. The MJO skill is really most strongly confined to the Indian Ocean, and then to a lesser degree, the seas around the Maritime Continent. And then there's virtually no skill in the equatorial Western Pacific. And the reason for that is that the MJO filter is a bandpass filter. So when you average over a long period, it has to have equal positive and negative anomalies. Whereas if you're in a strong El Nino, even the strongest MJO is probably only going to get you back to neutral. It's not going to get you all the way down to dry. So in a way, there are some tertiles that the MJO is just not going to be able to get during certain situations if the low frequency is too strong. Similarly, equatorial osprey waves are help out a bit in the Indian Ocean, but also show up fairly prominently in regions where you have a lot of tropical cyclone activity, like the Northwest Pacific, the Southwest Pacific, and the Atlantic. Equatorial osprey waves affect tropical cyclogenesis, but they also move at roughly the same speed as tropical cyclones, so there could be aliasing there as well. So now this is the same thing, but for the actual CFS forecasts. And so on the top row, that's just the raw, unfiltered anomalies from the CFS after doing the bias correction. And you can see that it looks a fair bit like the second row, which is the low frequency filter of the combined observations in CFS. And in fact, in the equatorial Western Pacific, the low frequency has more skill than the unfiltered. And so what that essentially means is that any weather, any MJO or equatorial waves or anything else that the model is producing is actually detracting from the skill. That in a sense, it would be better off just doing persistence of saying, look, we're in El Nino, it's going to rain, or we're in a La Nina, it's not going to rain. And I'll need to think more about this, but I suspect this is kind of tied to that week 1 versus week 4 variance that Ben was talking about. Meanwhile, if you look over the Indian Ocean, the MJO produces a little bit of skill with the CFS over the Indian Ocean, but in general, the CFS skill, the gray shading is not significantly different from 0. So for most of the tropics, the MJO is actually not significantly contributing to the rainfall skill in those regions. And equatorial osprey waves, it's basically never significant. However, if I add the modes together iteratively, so start off with just the low frequency in the second row, low frequency plus the MJO anomalies, and then add the equatorial osprey wave anomalies onto that. So adding these waves together, you get a little bit more skill in each case. And that kind of goes back to if you've got a really strong low frequency state, the MJO is only going to push you a little bit off of that. And so putting them together can give you a little bit better source of skill. But again, like in the equatorial Western Pacific, really anything you do makes it worse because that low frequency is just so strong. This was kind of another way of looking at it, was how far out could you forecast a 7-day running average before it becomes essentially indistinguishable from 0 skill. And over the equatorial Western Pacific, because of that really strong persistent signal, no matter what you do, you're going to be skillful out to the full 45 days of your forecast. Whereas in the Indian Ocean, The unfiltered, just the raw CFS gets you like a 3 to 4 week skillful forecast. The low frequency alone would not be able to do that. You really have to have the MJO in order to get that 3 to 4 week forecast skill in the Indian Ocean. And actually the Maritime Continent's another region where there's fairly good skill, although again, a lot of it comes from the kind of persistent signals. Here's yet another way of looking at it. So I've broken this up into 4 main regions, these blue boxes: the Indian Ocean, Maritime Continent, Western Pacific, and the Atlantic. And the dashed lines are averaged over the entire tropical strip. And these are the skill, the high skill scores for each of the different combinations of waves. So in most of these regions, the unfiltered is going to still be the best. That just using the raw model, the model kind of knows what it's doing, and that skill does decrease with time as you go farther out in lead time. But the other wave modes are generally below it, with the exception of the Western Pacific, where after essentially week 2, the low frequency is better than anything else. In the Indian Ocean, again, you get quite a huge bump by adding the MJO. So that blue line with the low frequency plus the MJO is quite a bit higher than if you were just doing the low frequency. In the Maritime Continent, it's kind of in between, where you get some of your skill from the low frequency, some of it from MJO. That kind of makes sense, where that's a region that's strongly affected by both. And then the Atlantic, there's no real particularly strong player over the others. So one more way that I'm going to look at this is how that skill of the MJO above and beyond what the low frequency gives you varies by season and region. So I'm going to show a few of these plots, and they're a little bit complicated, so I'll try to explain it first. Each row is a different lead time going from weeks 1 to 4. And then the x-axis is the 8 phases of the MJO, and then weak, medium, or strong, determined just by the amplitude, not looking at the phase at all. And then A is for all days, regardless of what MJO is doing. And then, of course, the 4 different seasons that we're looking at. So not too surprising, this one is for the entire tropical strip, 20 south to 20 north. As your MJO gets stronger, you tend to have more skill. The MJO tends to contribute more skill above what the low frequency would be doing. So the red dots are areas where the MJO, adding the MJO to the low frequency is helping your forecast. Blue dots are where it's actually hurting your forecast, where you'd be better off just using the low frequency. And large dots are statistically significant differences. And so again, as the MJO increases, you tend to get skill farther out in time. The MJO is particularly useful during the spring, which I think is when it tends to be the strongest, and also particularly when you're in phases 3, 4, and 5, which I think makes sense, because if you're in those phases, you don't have to worry about initiation in phases 1 and 2. You already have an MJO. You just have to keep propagating it along, and you don't have to worry so much even about what happens to it after it crosses the Pacific. During the summer, the MJO is actually not very useful. So the MJO actually decreases your skill in weeks 3 and 4, especially in some of the earlier phases. Looking at the Indian Ocean in particular, it makes sense that, again, the MJO tends to be very skillful there, again, especially during spring. It almost doesn't matter which phase you're in, but those earlier phases tend to be more skillful. Again, you do also have a decrease in skill at the longer leads in during the summer as well, though. But in general, it almost doesn't matter where or when you are the Indian Ocean, you're going to get a benefit from the MJO filtered anomalies. Maritime Continent's a little bit more mixed. Again, you have that strong signal in phases 3, 4, and 5 in the spring. Summer and winter, it's a little bit more scattered after week 1. And then during the fall, interestingly enough, the MJO kind of hurts your skill at longer leads. And I suspect this is tied to ENSO, where you're going to have perhaps stronger ENSO anomalies over the Maritime Continent during the fall. And so again, the MJO is not really going to be helping you that much in that region then. And then finally, the Western Pacific, again, surprisingly, not much skill from the MJO anywhere. There's a little bit in the summer if you're in the right phases, but it's still largely limited to week 1 or 2. And in the fall, it's really hurting you. And again, I suspect that's tied to strong variations in ENSO during the fall. And finally, for the Atlantic and South America, the MJO tends to help the most during the spring and summer, especially in phases 3, 4, and 5 again. And MJO actually kind of hurts things in the winter over the Atlantic. So kind of wrapping up, I'll go back to my main points. Again, it seems like a lot of the strongest skill for subseasonal forecasting in the MJO comes from these, or in the CFS, comes from essentially persisting the ENSO effects. And so, normally at this time on a Monday, I'm usually on the conference call with CPC when they're working on their global tropical hazards forecast. And what I try to tell the forecasters is to look at this image on my website and focus on the magenta contours, that low frequency, that essentially if it's been, in this particular case, it's been really wet over the Maritime Continent and the South China Sea for several weeks now. Pretty good bet that that's going to keep happening. You definitely put a dry shape over the equatorial Western Pacific associated with the La Nina. That's easy money, both of those. Then kind of after that, the next lowest hanging fruit are the MJO filtered anomalies, these black contours, where, especially when you've got contours over the Indian Ocean, that's particularly a higher skill thing to leverage. And then equatorial Rossby waves are a little bit more forecast of opportunity, where there's certain regions and seasons that they're helpful, but largely focusing on the low frequency and the MJOs is going to be where most of the skill comes from. So with that, I'll hand it back off and happy to take any questions.
Great, thank you, Carl. Let's see. No questions in the document right now, and I don't see any in the chat. If anyone has something that's just coming to mind, we have about 10 minutes, so if you'd like to make a comment or ask a question, you can go ahead and unmute yourself and ask. All right, well, we're not hearing any questions right now. So this is your last call. Okay, well, remember that because of the AGU meeting, we're not going to have a seminar in December, but it will come back in January, first Monday, unless the first Monday is New Year's. We'll have to look at the calendar, but first business Monday. at 2 o'clock Eastern Time, we'll have another webinar in January and continue on in the new year, first Monday of the month. So if you'd like to get on the mailing list and get the calendar invite, if you haven't already, you can email Karen Keith, karen.keith@noaa.gov. We have a Google site. Unfortunately, it's only accessible to NOAA folks right now. So if you have a NOAA email address, you can get to the site. We're grabbing the slides and we have the recording. So those will be made available after the fact if you have folks that you want to share it with. So last chance again for questions. Okay. Well, thank you everyone for attending this webinar. We will see you in 2 months. Have a great day. Thank you.
Thank you, Bonnie.